Welcome! Today, we'll tackle an exciting problem: find the derangement of an array. In this challenge, we'll explore strategies to compute a special kind of permutation where no element remains in its original position. Let's dive in. In this problem, we need to compute the number of derangements for an array of size n. A derangement is a permutation of the array such that no element remains in its original position. For example, if the array contains integers from 1 to n, a valid derangement would ensure that the element 1 is not in the first position, 2 is not in the second position, and so on. The result must be returned modulo 10⁻9 plus 7, as the size of the array can be as large as 1 million, making the result potentially very large. The input consists of a single integer n where n ranges from 1 to 10⁻6, and the output is a single integer representing the number of derangements. Let's explore some examples to better understand this concept. Consider the case where n is equal to 3. The array 1, 2, 3 can be rearranged in such a way that no element appears in its original position. For example, 2, 3, 1, and 3, 1, 2 are both valid derangements, as all elements have been shifted to different positions. In total, there are 2 valid derangements of the array of size 3. Therefore, the output in this case is 2. This example highlights how we count only the permutations that satisfy the derangement condition. Now, for n equals 2, the array 1, 2 can be deranged in only one way: 2, 1. In this arrangement, 1 is not in the first position, and 2 is not in the second position, satisfying the derangement condition. As there is only one such arrangement, the output is 1. This demonstrates that smaller arrays have fewer possible derangements compared to larger ones. When n equals 1, the array 1 contains only a single element. It is impossible to rearrange this array such that the element 1 is not in its original position because there are no other positions available. As a result, there are no valid derangements, and the output is 0. This serves as the base case for our problem, where the smallest input size has no derangements by definition. To efficiently compute the number of derangements for larger values of n, we use a recursive formula. The base cases are defined as 1 equals 0, since no derangement exists for a single element, and 2 equals 1, as there is only one valid derangement for 2 elements. The recursive formula for n is given by n1 asterisk n1 plus n2. This formula ensures that we count all derangements while adhering to the condition that no element remains in its original position. However, since n can be as large as 10⁻6, directly computing this recursively would be inefficient. Instead, we apply dynamic programming or an iterative approach to compute the result efficiently. Additionally, modular arithmetic is used to keep the computations manageable and prevent overflow when dealing with large values. This approach ensures that we can handle the constraints of the problem effectively. To begin, we can consider the brute force approach as the simplest way to solve the problem. The idea here is to generate all possible permutations of the array 1, 2, n, and check which of them satisfy the derangement condition, meaning no element remains in its original position. For example, in a permutation, the value at index I should never be equal to I. This can be done using backtracking to generate all permutations and then verifying each one. However, the main drawback of this approach is its inefficiency. Generating all permutations takes factorial time, O(n), and verifying each permutation adds an additional O(n). As a result, the total complexity becomes O(n). *n, which grows extremely quickly as n increases. This makes brute force impractical for large arrays, especially since it does not take advantage of mathematical patterns and derangements that could simplify the process. Now, let's explore a more efficient strategy using a recursive formula based on a well-known mathematical property of derangements. We denote d(n) as the number of derangements for an array of size n. The recurrence relation for d(n) is given by d(n) equals n1 asterisk d(n1 plus d(n2), with base cases being d(1 equals 0 and d(2 equals 1). To understand this, consider an array of size n and focus on the first element, for instance 1. If you place 1 in position k where k equals 1, there are 2 possibilities: either the element originally at k, let's call it x, is placed back in position 1, in which case the remaining n2 elements must form a derangement, contributing d(n2), or x is not placed in position 1, meaning the remaining n1 elements other than 1 must form a derangement, contributing d, n1. Combining these two cases gives us the recurrence formula. Using this recursive approach with memoization to avoid redundant calculations, we can compute d, n, efficiently in O, n, time, with a space complexity of O, n, for the memoization table. Next, we can further optimize by using an iterative dynamic programming approach instead of recursion. Here, we compute d, n, iteratively, starting with the base cases d, 1 equals 0 and d, 2 equals 1. For each I from 3 to n, we calculate d, I, using the formula d, I, equals, id1, asterisk, d, id1, plus d, id2. This eliminates the overhead of recursive function calls and simplifies the implementation. In terms of complexity, the iterative method also runs in O, n, time, but the space complexity can be reduced from O, n, to O, 1, by maintaining only two variables to store the values of d, I1, and d, I2. Additionally, for large values of n, the result can become very large, so we use modular arithmetic to ensure that calculations remain within a manageable range. By taking results modulo 10⁻9 plus 7 at each step, we prevent integer overflow and ensure the solution meets the problem's constraints. The chosen strategy for this problem is the iterative dynamic programming approach. This approach strikes an excellent balance between simplicity, efficiency, and scalability. Unlike brute force, which is computationally infeasible due to its factorial time complexity, or recursion, which risks stack overflow without careful optimization, iterative DP avoids these pitfalls. It achieves linear time complexity and can be implemented with constant space by keeping only the last two states in memory. This makes it particularly well suited for large N, where reducing both time and space complexity is critical. Another key advantage is the seamless integration of modular arithmetic, ensuring correctness for large inputs. The iterative method directly leverages the predictable mathematical pattern of derangements, avoiding unnecessary computation like generating all permutations. This efficiency, combined with its robustness, makes iterative DP the most practical and optimal solution for this problem. The problem we're solving is to find the number of derangements for an array 1, 2, n. A derangement is a permutation where no element appears in its original position. To start, we can use a brute force approach. This involves generating every possible permutation of the array and then checking if each permutation satisfies the derangement condition. To generate permutations, we use backtracking. We maintain a list to construct the current permutation and an auxiliary array to track which elements have been used. At each recursive step, we consider every unused element, add it to the current list, and proceed further. Once a permutation is fully constructed, we backtrack by removing the last element and marking it as unused. After generating a permutation, we validate it by ensuring that for every index I, the element at permutation, I, does not match its original position, I plus 1. To keep track of valid permutations, we maintain a counter, incrementing it for each permutation that satisfies the derangement condition. Once all permutations are processed, the final count is the total number of derangements. This process can also be expressed as pseudocode. Using Python zittertools.permutations, we generate all permutations of the array 1, 2, n. For each permutation, we check that no element is in its original position using a simple condition. If the condition holds, we increment the count. Finally, we return the count of valid derangements. While this approach is straightforward and easy to understand, it's inefficient for large values of n due to the enormous number of permutations generated. The brute force method has significant computational drawbacks. Generating all permutations has a time complexity of O, n, and checking each one for the derangement condition adds another O, n, work per permutation. This leads to an overall complexity of O, n, asterisk n, which quickly becomes infeasible as n grows. For instance, when n equals 10, the number of permutations exceeds 3.6 million. Despite its simplicity, this approach is not practical for large inputs. However, it serves as a useful baseline and is effective for small inputs. To overcome these limitations, we can turn to a dynamic programming approach. Dynamic programming allows us to efficiently compute the number of derangements in O, n, time by leveraging a recurrence relation and avoiding redundant computation. The dynamic programming solution begins by defining the state. Let dp I represent the number of derangements of an array of size I. Next, we establish the base cases. When I equals 1, no derangement is possible, so dp 1 is 0. For I equals 2, there is exactly one derangement, 2, 1, so dp 2 is 1. For larger values of I, we derive a recurrence relation, dp I equals I1 asterisk dp I1 plus dp I2. This formula accounts for two possibilities. First, the chosen element swaps with the first position, leaving I1 elements to be deranged, which corresponds to dp I1. Second, the first and swapped elements are fixed, reducing the problem to deranging I2 elements, which corresponds to dp I2. Using this relation, we can compute dp I iteratively for all values up to n. Once the recurrence relation is defined, the implementation becomes straightforward. We initialize the base cases, dp 1 equals 0 and dp 2 equals 1. Using a loop, we calculate dp I for all values from 3 to n based on the recurrence formula. Finally, the value of dp n gives the total number of derangements for an array of size n. The pseudocode demonstrates this process clearly. This approach is efficient because it avoids the factorial growth of permutations seen in the brute force method. By leveraging the mathematical insights from the recurrence relation, we reduce the problem to a series of linear computations, making the algorithm suitable for much larger values of n. To implement the dynamic programming solution efficiently, we use an array dp to store the number of derangements for array sizes from 1 to n. This allows us to iteratively compute results without recomputing subproblems. However, we can optimize space usage further. Observing that the recurrence relation only depends on the last two computed values, we replace the dp array with two variables, previous 2 for dp I2, and previous 1 for dp I1. Using these variables, we compute the current value and update the previous values iteratively. This reduces space complexity from O(n) to O(1). The optimized pseudocode highlights this approach, where we maintain just two variables while iterating through the required computations. The optimized dynamic programming solution has a time complexity of O(n), as we compute the result with a single loop from 3 to n. Its space complexity is O(1), since we only store two intermediate values at any given time. In conclusion, while the brute force approach is simple and intuitive, its inefficiency makes it impractical for large inputs. The dynamic programming solution, on the other hand, demonstrates the power of mathematical insights and recurrence relations. By reducing the time complexity to O(n) and space complexity to O(1) in the optimized version, this solution highlights how algorithm design can transform a computationally expensive problem into one that is highly efficient and scalable. This implementation solves the problem of finding the number of derangements for an array of size n using dynamic programming with a space-optimized approach. A derangement is a permutation where no element appears in its original position. The problem relies on a mathematical recurrence relation, dn equals n1 asterisk dn1 plus dn2 asterisk asterisk, where d0 equals 1, conceptual base case, representing an empty set. d1 equals 0, you cannot derange a single element. Explanation of the code. 1. Edge case handling. If n equals 1, the function immediately returns 0 since there are no derangements for a single element. 2. Modulo constant. We define mod equals 10 to the power of 9 plus 7 to ensure that the result does not exceed the constraints of large numbers, as required by the problem. 3. Base cases initialization. Previous 2 is initialized to 1, d0. Previous 1 is initialized to 0, d1. For iterative calculation. Using a for loop, we compute the derangements iteratively from 2 up to n. At each step, we calculate current using the recurrence relation and update the previous values, previous 2 and previous 1, accordingly. 5. Return result. After completing the loop, previous 1 contains the value of dn, which is returned as the result. This approach is efficient with a time complexity of O(n) and a space complexity of O(1), since we only store the last two computed values. This makes the solution suitable for large inputs up to the constraint limits. This is the Java implementation of the Find the Derangement of an Array problem from LeetCode. It mirrors the Python logic using a dynamic programming approach to calculate derangements efficiently. Key differences include explicit type declarations for variables, use of the long type to handle potential overflow during intermediate calculations, and casting the result back to int for the return value. The modulo operation ensures results fit within the constraints, and the iterative approach maintains memory efficiency. The goal of this problem is to compute the number of derangements for an array consisting of integers from 0 to n1. A derangement is simply a permutation where no number is in its original position. For instance, when n equals 3, valid derangements include 1, 2, 0, and 2, 0, 1, as no number stays in its starting position. To solve this problem efficiently, we use a recurrence relation, d, n, equals, n1, multiplied by the sum of d, n1, and d, n2. This formula is derived from the observation that for each element in the array, we can swap it with another element and then recursively solve the remaining subproblem. Additionally, since the results can grow very large, the final answer is taken modulo 10 to the power of 9 plus 7. To illustrate how the recurrence relation works, let's start with a simple example where n equals 2. First, we define the base cases, d0 is 1, as an empty set has only one way to be considered deranged, and d1 is 0, as a single element cannot avoid its original position. We initialize two variables, previous 2 as 1 and previous 1 as 0, to store the results of d0 and d1, respectively. Now, for I equals 2, we compute d2 using the formula d2 equals 2 to 1 times the sum of previous 1 and previous 2. Substituting the values, d2 equals 1 times 0 plus 1, resulting in 1. After this computation, we update our variables, previous 2 becomes previous 1, which is 0, and previous 1 becomes the current result, 1. Finally, we return d2, which is 1. Now let's extend this to n equals 3. We again start with the base cases, d0 is 1, d1 is 0, and initialize previous 2 to 1 and previous 1 to 0. First, for I equals 2, we compute d2 using the recurrence relation. Substituting the values, d2 equals 2 to 1 times previous 1 plus previous 2, which simplifies to 1 times 0 plus 1, giving us 1. We then update previous 2 to 0 and previous 1 to 1. Next, for I equals 3, we calculate d3 as 3 to 1 times the sum of previous 1 and previous 2. Substituting the updated values, d3 equals 2 times 1 plus 0, resulting in 2. After this computation, previous 2 is updated to 1 and previous 1 to 2. The final output for this example is d3, which equals 2. For n equals 4, we follow the same process. Starting with the base cases d0 equals 1 and d1 equals 0, we initialize previous 2 as 1 and previous 1 as 0. For I equals 2, we compute d2 as 2 to 1 times previous 1 plus previous 2, which gives 1 times 0 plus 1, resulting in 1. We then update previous 2 to 0 and previous 1 to 1. For I equals 3, d3 is calculated as 3 to 1 times previous 1 plus previous 2. Substituting the values, d3 equals 2 times 1 plus 0, yielding 2. We update previous 2 to 1 and previous 1 to 2. Finally, for I equals 4, we compute d4 as 4 to 1 times previous 1 plus previous 2. Substituting the updated values, d4 equals 3 times 2 plus 1, resulting in 9. After this step, previous 2 becomes 2 and previous 1 is updated to 9. The result of d4 is therefore 9. This means that there are 9 distinct ways to derange an array of size 4 such that no element appears in its original position. By following the recurrence relation and iteratively updating the variables, we can efficiently compute the number of derangements for any given n, while ensuring that the result is returned modulo 10 to the power of 9 plus 7 to handle large values. The time complexity of this solution is O(n), where n represents the input value. This comes from the loop that iterates from 2 to n, inclusively, resulting in approximately n1 iterations. When simplified, this is O(n). Inside the loop, the operations performed are all constant time, or O(1). For example, the computation of I1 and asterisk, previous 1 plus previous 2% mod involves basic arithmetic operations like addition, multiplication, and modulus, each of which takes constant time. Updating the variables previous 2 and previous 1 also happens in O1 time. Since the loop dominates the runtime and performs constant work in each of its O(n) iterations, the overall time complexity is determined to be O(n). The space complexity of this solution is O1, or constant space. This is because the algorithm only uses a few variables to store intermediate results. Specifically, previous 2 and previous 1 are used to hold the results of the previous 2 states in the recurrence relation, while current temporarily stores the result for the current iteration. Additionally, mod is simply a constant used for modular arithmetic. No additional data structures, such as arrays or lists, are required, and the memory usage does not depend on the size of the input n. As a result, the space complexity remains constant at O1. To compare, a brute force approach to this problem would involve generating all possible permutations of the array and verifying each one to check if it meets the derangement condition, where no element is in its original position. Generating all permutations would require O(n) time, and verifying the derangement condition for each permutation would take O(n) time. Therefore, the total time complexity for the brute force method is O(n) asterisk n, which becomes computationally infeasible as n grows. In contrast, the optimized dynamic programming solution uses the recurrence relation d n equals n1 asterisk d n1 plus d n2. This allows us to iteratively compute the result in O(n) time in O1 space by keeping track of just the last 2 results. This optimization represents a dramatic improvement over the brute force method. In every case, whether best, average, or worst, the solution consistently involves iterating from 2 to n, performing a fixed amount of work in each iteration. As a result, the time complexity remains O(n) across all scenarios, and the space complexity is always O1. To mathematically prove the big O bounds, consider the time complexity. The loop runs for n1 iterations, with each iteration performing O1 operations. This simplifies to a total of O(n). For space complexity, only a constant amount of memory is used throughout the algorithm, regardless of the size of n, which confirms the O1 space complexity. This consistency ensures the solution is efficient and scalable for any input size. When tackling derangement problems, there are a few common mistakes to watch out for. First, many beginners confuse permutations with combinations. Remember, permutations are all about order, it matters where each element is placed. In a derangement, we're looking for specific permutations where no element is in its original position. Treating it like a combination problem, where order doesn't matter, leads to invalid solutions. Another frequent issue is relying on brute force for large inputs. Generating all permutations and checking for derangements becomes computationally impractical as the input size grows, because the number of permutations grows factorially with n. This exponential growth makes naive approaches infeasible for larger arrays. Lastly, failing to account for edge cases like small inputs such as n equals 1 or 2, empty arrays, or duplicate elements, can lead to runtime errors or incorrect outputs. Edge cases often reveal hidden bugs, especially in recursive or dynamic programming solutions, so handling them carefully is essential. Another common challenge is misunderstanding how to implement recursive solutions effectively. Recursion can be powerful for derangement problems, but it's easy to go wrong by neglecting base cases or failing to optimize with memoization. Without caching intermediate results, recursion can lead to redundant computations and stack overflows, particularly for larger inputs. This makes the solution both slow and resource-intensive. In addition, many miss the opportunity to use mathematical insights, like the inclusion-exclusion principle, or turn to direct combinatorial formulas. These approaches often provide much faster and more elegant solutions compared to brute force. Overlooking these constraint-based methods is a missed opportunity to significantly improve efficiency, as they can reduce the complexity from factorial to linear or polynomial time in some cases. Recognizing when to apply these principles is key to solving derangement problems effectively. In interviews, it's important to recognize patterns in problems, as many challenges are variations of classic combinatorial tasks like derangements or permutations. Quickly identifying these patterns helps you focus on the right approach. A common trade-off you might discuss is iterative versus recursive solutions. While recursion is often easier to write and understand, it can be risky for large inputs due to memory constraints and stack overflow risks. Iterative approaches, on the other hand, tend to be more robust. Optimization is another area interviewers often evaluate, so breaking the problem into smaller subproblems is a valuable strategy. For example, the recursive formula for derangements, dn equals n1 times the sum of dn1 and dn2, reduces the problem size step by step. Don't forget to clarify edge cases with the interviewer before coding. For instance, you'll want to establish the expected output for n equals 0 or other invalid inputs. Additionally, practicing related problems such as generating permutations or solving combinatorics challenges can help you recognize and apply the right techniques more effectively. There are 3 alternative approaches to solving derangement problems, each with its own trade-offs. First, dynamic programming offers a bottom-up approach that uses the recurrence relation to compute derangements iteratively. This avoids the pitfalls of recursion, such as stack overflow, and is generally easier to debug. However, it may require extra space for the DP table. Another option is leveraging the inclusion-exclusion principle to directly compute the number of derangements using a mathematical formula, dn equals n factorial times the alternating sum of reciprocal factorials. This method is extremely efficient and elegant, but deriving and explaining the formula can be challenging, especially in an interview setting. Finally, backtracking with pruning is another intuitive approach. Here, you generate permutations and skip branches where an element is placed in its original position. While this method is conceptually simpler, it tends to be less efficient compared to dynamic programming or direct formulas, especially for larger inputs. Choosing the right approach depends on the problem constraints and the context in which you're solving it. Great job! Today, we learned about derangements and uncovered different strategies to solve this intriguing problem. Remember, understanding the fundamentals and practicing are key to mastering such challenges. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!